Well, greetings, Tim Tomians. This is Tim here, just playing around with some DC voltage losses. That's what this rat's nest is here, but I have one of these, and I thought this is a pretty nice little distribution panel. It seemed to give you a lot of wire here. Wire here. I don't know, it probably comes out to be, I guess that's about 8 foot, maybe when you straighten out, at least 6 foot, I'd say. Goes up into here, feels like maybe number 10 wire. It's got a an ammeter and some banana jacks. So one of the things that I've noticed about this, not just on this, but on just about everything, is these banana jacks, you know, you put a connector on it, like a spade connector of some type, and it just never seems like you can get them tight enough. And in fact, you know, that's pretty darn tight, but look at how loose that is. I mean, that is basically falling out of there. So I think what I find is that the actual metal part doesn't stick up past the nut enough, and I'll show you what I mean. But if you take these off, and they're almost impossible to get off because they damage the thread at the end, so they don't fall off. But if you take these off, maybe you could put a washer in there, a thin enough washer that would beef up the area, the surface area for where the conductor is, not the plastic. It's almost like the conductor's inset into the plastic too much. So what I did was, if you look at this one, I put banana jacks, and I don't really know what the rating of the banana jacks is. I think in general they're somewhere between 15 and 20 amps. I know you can get higher rated banana jacks and blah, 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 blah. But these banana jacks were able to accommodate a number 12 wire. So I'm assuming they can at least handle 20 amps. And that's not going to be a continuous power consumption anyhow, you know, with the radio. But even here, these are those big wires you look in here. They have the wire nuts coming, but even pushing in the direction of tightening, they're not really clamped down that hard. And look, I can pull this right out of here. And those were tightened down there pretty darn good. Let me make sure everything's turned off. I'm gonna pull this out without even, look, I pull them out without even loosening them. But I'll show you, maybe I can show you what my belief is here. And these were, you know, these were Amazon purchases, but certainly I'm sure that they're not lab quality or something. I'm going to turn a light on here, see if we get this lit up a little bit more inside there. But my belief is that the conductor part in here, the metal, it actually sits, it looks like it almost sits perfectly level with the plastic. And then on the cap end, I just don't know if you can see in there, it actually looks like it's, I can't, try and zoom in a little bit. All right. On the cap end, it's actually, the conductor sits in there. So it's going to mainly be plastic on plastic when you tighten your stuff down, these connectors here. So where are they? Let me zoom back out. Yeah, they're going to be get my finger out of the way. They're going to be plastic on plastic, or at least plastic holding to this, and then I don't know. That's not a real good method. And again, maybe it's just because these aren't top of the line banana jacks, but I'm finding that on more than just this. It's on that, and it's even on the other power supply I had. So just something to think about. These, and I know you can get them at different ratings. One thing I don't like about them is, you know, that they can easily be pulled out. Not easily, but they can be pulled out. course, normally when I have this, I have the big power supply in here, and I'm just trying this one out. But I usually have my big linear power supply here, so you can't get back here to pull these out. Now these ones, the little ones, seem to be better. They're not moving around like that. Well, my famous last words. But these big ones definitely, look, and I mean that's tightened down in there. So anyhow, just something to think about when you're wiring your DC stuff. Maybe find a more permanent solution. But I know, anyhow, back to it, when I plug these banana jacks into here, the ICOM's only putting out about 75 watts. When I remove the banana jacks and plug them straight into the power supply, I get the full 100. Is it because of the loose connection here, or the loose connection here, the length of wire, or I don't know really what's behind this? I would imagine that the negative comes up and goes straight to these, and then through this, well, probably straight to these and straight across to that, and then the positive, the red goes through the ammeter, then to these, and in parallel there's a switch for these guys, because these guys are all, you can switch these ones. These ones are unswitched, as it says right there. All right, so one possible solution is, you can see there's a hole here in the binding post, and it's, in this case, it was thick enough to accommodate one side of this. Again, that's leaving a whole lot to be exposed now. You know, something could fall in that. But it's a good tight connection. However, it still does not, even when I plug the banana jacks into here on the ICOM, I'm still only getting about 75 watts through that. Again, could it be that lossy because of all this cable back here for that? All right, so I pulled the cover off there, and we'll take a quick look in here just to see if anything's loose. Nothing really stands out. I don't like that there's not a grommet, a rubber grommet back in here. You know, if you're running 25-30 amps through this thing. Let's see, it's got some fuses going through here. Here's the, I don't know what's up with that. Look at it through the phone. Here's the shunt for the ammeter. The ammeter's off a little bit. I don't really know how much we can really do about that. And then these would be the terminals where the high current goes through, and it looks like it's got a series of fuses for those two. So they are fused. We at least know that. See anything else. I just wanted to make sure that maybe there wasn't a loose wire or something.
Newspapers get recycled.
Alrighty, well, I guess if you're really serious about squeezing every bit of power you can, you might want to cut this. You probably bet you I could cut at least 3 feet out of it. Comes out through there, goes around through here, and the other power supply, the connectors are back here, right about here. So I'm just really hesitant about cutting wire that's this thick, because you know it'll be expensive to replace, and if I cut it an inch too short. But anyhow, measure twice and cut once, I guess. But something to check. Check your voltage at your radio if you go through things like this. It's a nice distribution center, but if it robs you of DC power, well, that's going to rob you of RF power in the long run. So All right, so we can figure out maybe where the extra current's going. So here we're going to simulate. I have two 25 watt. I just picked the biggest resistors. I have two 5 ohms in parallel. So in parallel. So that'll come out to be actually 2.5 ohms. And then over here, I'll show you when I measured them. Here's the ohm meter. You can see here. I'm going to put this on here. It was somewhere between, no, it's 2.6. Somewhere between 2.4 and 2.6. All right, so here we have two 5 ohm resistors equals 2.5. And then remember Ohm's law, voltage divided by resistance equals I, or no, that was intensity, but equals current, amps. So 13.8 volts, which is what this power supply puts out, and we'll show you that in a minute. And we just calculated, actually measured it at 2.5 ohms and 5.52 amps. So that's what we should be getting. So let me plug this back in. I'm back here where the connections are for the power supply. They just come straight up to here. I'm going to turn this on, make sure. Got 13.8 volts there. And here we're showing that we're getting 5.58 amps right there. So pretty darn close. That's Ohm's law at work. Okay, so what happens when we introduce a bunch of wire into the equation? Let me get that all in place. All right, even though I'm using regular extension cord, you can see how this mess is here. That's about, probably about 40 feet of extension cord, just all different type. And it's thinner stuff. I didn't want to use heavy duty cord just to see what happens. And I don't have any connection to it yet except for the, that's not 110. That's just the 12 volts coming from the power supply. All right, what were we seeing here? Put these guys back on here. That's showing 13.7, and that's 13.8. So pretty accurate still. Okay, so now we're zero there. We'll throw it back on. It's going to move around a little bit, just, and now it's back at 0.03, but that's okay. We're mainly worried about the 13.7 and the 13.8. Now let me turn this back off, and I'm going to make my connections here. My two resistors are going to come over, and they're going to connect onto these paper clips. Kids, don't try this at home. All right, so looks like on one side we have the red and green, and on the other side we have the black and yellow. And in theory, if I made a good connection when I turn this on, we should start to see some numbers. Hopefully my wires don't melt immediately. All right. Showing 7.4, 7.7, something like that. Look at the current we're drawing up here. 2.4, remember that, I'll write that down, 2.4 amps and 785 volts. Okay, we're still good to go. My wires aren't starting to melt yet. So how about if we put this out in the field? Let's take that off there. Let's put this down here on, we're gonna put it on the black, or how about I wanna place it on the green and red wires. Let's see what happens. 2.4 something, 2.5. So about 2.5 amps. So out here, it's saying we're drawing about the same kind of current as we are out here. Yet the voltage dropped because all this length of wire here, the voltage dropped. So you're thinking to yourself, well, if the voltage dropped, wouldn't the current go up? Because that would account for keeping the power consumption the same. But don't forget, all these wires are series resistance. So let's check this and see what we get for resistance. Let me unpull these leads off here and connect my meter to it. So let me do that, and I'll be right back. All right, I changed the connection there. Got 5.5 ohms total resistance. 5.5. So let's try Ohm's law and see what we get with that. 13.6 divided by 5.5. So it comes out with about 2.47 amps. So we know that the two resistors here equal 2.5. So this must be 3. So each, there was about another 1.5 ohms just in the wiring itself that posed a little bit of an issue to us. So that would be if you series it, 1.5 and 1.5 is 3, and this is 2.5. So that's 5.5. So that's about what that comes to be. Oddly enough, and I know it's the resistors, but as they're cooling down, the resistance is actually starting to go up. So now let's just confirm. I'm going to short these, take these off and short these two, and make sure that we have about 3 ohms according to the ohm meter. Now, there's one, and that'll confirm that our wires come up to, well, no, that's saying about 4.3. So that's just the wiring is 4.3. So that's where a lot of your resistance gets, or a lot of your voltage gets chewed up, because remember, in a series circuit, it starts off with your full voltage here, and there's a voltage drop across each one of these, which is current times resistance, minus it, minus it, minus it. By the time you get back here, you have 0. So the longer your wire, the more resistance you're going to have there, and the more voltage drop you'll have across that. All right, well, I hope that explained everything and made it clear as mud. But the main takeaways here are, when you're calculating this, don't forget the wire from the or the resistance from the wire, because that kind of becomes pretty substantial. Say in that, what do we got? I don't know, we'll say 40 feet of wire here. You're probably losing close to half of your voltage. So it would be 3 ohms times the current. So that's pretty substantial. So again, something to think about. Thanks for watching. Hope you enjoyed it.